This video is on a technique called mass spectroscopy. Mass spectroscopy is a method of determining the relative abundance of isotopes. Essentially, you weigh the ions in the gas phase. It's based on physics. Heavier objects do not corner as well as lighter objects. And in actuality, it can be used to help identify molecules, but that's beyond the scope of this course, so we won't deal with this. And we're going to start with an analogy. Assume you have a Kenworth cab and a smart car for two. The Kenworth cab weighs markedly more than the smart car for two. We're going to send both of these vehicles through a track which is curved 90 degrees and see where they hit on a barrier. So they're going to head to the start line. We're going to assume they cross the start line at the same time. They will travel the same speed and they will start off right next to each other, just millimeters apart. When they hit the curve, they are going to steer an identical amount. And as you can probably guess, they start off right next to each other. But the smart car for two, being lighter, it can corner more quickly, and so it makes a tighter turn, and we see that the smart car for two will hit the barrier to the left of the Kenworth cab. Mass spectroscopy works in a similar manner. The sample enters here. Now the sample needs to be ionized, and that happens here. The ions advance into an area where they are accelerated, so when they exit here, they're traveling the same speed. Now, since ions have an electronic charge, they will be affected by a magnetic field. They don't have steering wheels, so the magnet is used to steer the ions. Lighter ions can steer the most or can deflect the most, and so down the road, you can see that you will have various ions striking at various places on the detector. The detector counts how many hits at each spot and can develop a bar graph which looks like this. And on the y-axis, you'll have the relative abundance. And on the x-axis, you have what is called the mass to charge ratio, sometimes written as m over z. But m over z, the mass to charge ratio, is essentially the mass number. So let's take a look at that bar graph. And what we see on this bar graph, which happens to be of zirconium, is there are 5 peaks. So we know there are 5 naturally occurring isotopes of zirconium with mass numbers of 90, 91, 92, 94, and 96. So we write that down. We can then look at the graph and read off the relative abundance. This portion, just a little bit above 50, below 60, so I would call that 51%. I take a look at this one. It's way below 10, but it's, I think, more than 1. I'm going to call that 2%. And I do the same for the other 3, and this is what I get for my values for my abundances. And in actuality, it turns out that if you do this with a better scale over here, these are the actual values you get. You've got germanium. The mass spectrum is here to the right. What is the atomic mass of germanium? I'm going to ask you to stop, figure out your answer, come back, check it, and then we'll go through it. Go. And the correct answer is 72.7 grams per mole. How do we do this? Well, I'm going to be doing a weighted average. So I'm going to lay out what I need. I'm going to look at my isotopes, my mass number, my percent abundance divided by 100, so I can calculate my relative weight. And the first thing I see is there are 5 isotopes. Germanium 70, 72, 73, 74, and 76. So I know my mass numbers. I go over the graph and I see the germanium 70 seems to be right at the 20 mark. So I'm going to read all of my various percentages off, and I divide them by 100, and so I get these values. And I know if I multiply the mass number times the percent abundance, I get the relative weight. I add those up, and I get the atomic mass. And if you go to your periodic tables, you'll see that the value is actually 72.64. So even with this crude graph, we do pretty well. So one more problem, it's a little more detailed. Chlorine, a diatomic molecule, has 2 naturally occurring isotopes. The mass spec of the Cl2 is given here. 2 questions. What are the mass numbers of the 2 isotopes, and which isotope is more prevalent? And please explain your logic. Stop answer the questions, come back, and we'll go through it. Go. And the correct answer for the first question is 35 and 37. How do we get that? Well, we know that there are two isotopes. Let A be the lighter isotope, B the heavier isotope. So now there are three possible combinations: A2, AB, and B2. And A2 would be this peak, AB is this peak, and B2 is this peak. So if I take my lighter peak, the A2 peak, I know that there are two chlorines in there, so 70 divided by 2 is 35. I go to my heaviest number here, which is 74, divide that by 2, and I get 37, so those must be my two isotopes. And actually, when I add the two of them up, I get 72, and so that seems to check out. So 35 and 37 are the two isotopes of chlorine. Which of the isotopes is more prevalent? Well, the chlorine 35 is more prevalent than the chlorine 37. How do we know that? This spike here is much bigger than this spike here. Then the chlorine 35 must be more prevalent than the chlorine 37. So that's how you use mass spectroscopy. Remember, it's a method of weighing ions in the gas phase. It allows us to determine the relative abundance of isotopes. And the graph is relative abundance versus the mass to charge ratio, but the mass to charge ratio is essentially the mass number. So now you know how we determine the percentage of isotopes. You can do your practice problems, and we'll move on to something new next time.